All right, ladies and gentlemen, thank you very much. So before I forget, let's just start off with the code for those who are watching the lecture late, and to fill in the late attendance form available on the YouTube description. Also, just to note that let's just start sharing. We did send out an email today containing a list of all of the important resources that you have access to, just a reminder, as well as details of the semester test and procedures that are followed on the various systems. So just because some people have registered late and maybe they didn't catch up by watching previous lectures like they should have, or for whatever reason they didn't seem to know what the process was or what they had available to them, we sent out a big email with that to everyone, as well as people who, according to our records, aren't participating meaningfully in the course. A warning letter was sent out today telling them that they need to increase their participation in the course in terms of lecture attendance, either live or, if necessary, via the late viewing links, and then also by doing VPL assignments and regular weekly practical assignments. So if you received such a letter, please take that as an indication that you need to do a bit more, a lot more. And there's still time. I mean, at this exact moment in time, if you start working hard, you can still get 100%. The VPL will allow you to make up for any practicals that went badly at this point. The semester test is still next week. You still have time, but start working right away. All right, let's continue with functions. And we were looking at functions with default arguments. So you can specify a value that the parameter will take if you don't specify any arguments. So also just to clarify, the terms that we sometimes use, the value that we pass to a function when we call it is often called an argument, and the value that it will take in the implementation of the function is its parameter. Technically speaking, they're actually all called parameters. These are called the formal parameters, and these are called the actual parameters, but it's incredibly common in programming to refer to these as the arguments. So sourborn in this case would be an argument, and str message would be a parameter. So that's by far the most common terminology, although technically speaking, the str message is a formal parameter, and sourborn in this example is an actual parameter. So can we have functions that have the same name? Well, the answer is we can, but with certain restrictions, and it has certain meanings. So functions can have the same name provided that their parameter lists differ. So that means that they can differ in terms of the number, order, and type of the parameters. So here's two examples of functions called larger. One takes two integers and returns the larger of those two integers, and the other one takes two strings and returns lexicographically the larger of those two strings. You can see that it's not an issue because the parameter lists differ in terms of the types of the parameters. The return types, one being integer and the other one being string, aren't used to differentiate between the two functions, because you could have an ambiguous case, for example, where a function is returning an integer and it's being used in a context where, say, a double could be used. Then it would be ambiguous as to which of the two is being used. So this phenomenon is called overloading. I've heard some activity on the stream. Let me take a look. So the dates for all of the practicals, all of those things are available on Eve. And if you're on computer, it's got a built-in calendar, so you should know when it is in this case. Why is it referred to as overloading? That's a good question. I don't actually know why they came up with that term overloading. As you'll learn next year, there are a lot of, not next year, in next semester, there's a lot of similarly named but subtly different things, overloading and overriding and redefining of functions. I'm not sure exactly why they came up with the term overloading of the function. I don't know. It's a good question. I don't have an answer for that. Never really thought about it, but if I do find out, I'll let you know. And if you find out, please let me know. I am now curious. But anyway, the phenomenon is called overloading. So formally, it's when two functions have the same name, or a set of functions have the same name, but differ in terms of their parameter lists, in terms of either the order, number, and type of the parameters. It's actually a typo over here. There should be an extra int over there. I'm not quite sure what happened, so please note that there is actually an error there. That should be int, and in front of int b, and yeah, just bear that in mind. Okay, in modern C++, I said that the boundary between modern and sort of classical traditional C++ is the C++ 11 standard. It introduced the ability to have functions that have an unknown number of arguments. Technically, you could always do it in C++, but by using the technique that C used originally, the language that C++ evolved from. So there's a couple of techniques that you can use to have functions with variable numbers of arguments, unknown number of arguments. One is that C technique, and that's number 2 there, which is considered unsafe now and not a good idea to use. And then there's another technique which you could use, but it relies on something called template-based metaprogramming, which is, we'll cover templates in the second semester. And then the other one here is to use a type you've actually already seen when we took a look at in the tutorials working with arrays, and in the video lecture that I posted relating to Practical 4. When you can use initializer lists to initialize arrays, you can use these same initializer lists to kind of do variable length arrays. It's not really brilliant. Variable length parameter lists. It's not really what's happening, but it sort of kind of feels like it. So we'll take a look there. So if let's say we had a function where we wanted to add a number to a list of values. Well, we could do that, but we can specify the remaining parameters to be an initializer list, which is a built-in type in the initializer list library. So you can see we have to add the hash include initializer list preprocessor directive. Then that type becomes available to us. It's also in the standard namespace, needless to say, but we will using namespace standards, so that doesn't really matter. And then you can work with it as if it were a collection like a string, and you can loop through it with a for each loop, for example, and do whatever you want with it. However, when you call the function, you then would need to specify using the initializer list notation. So technically, it's only 2 parameters. One of them happens to be a list, which gives you the arbitrary length that you want. Okay, let me just check what the remaining points were. It's very similar. So we will actually take a look at vectors as a contrast to fixed length arrays next week. Obviously not on Tuesday, because that's your semester test, but in the other tutorial sessions in class. So it's not a vector, but they're very closely related, and you can use them interchangeably in a lot of contexts with vectors. So that is a good observation. There's nothing that is due this week, although there is a practical session on Friday where you can ask questions, and we will have an exercise on Friday due the Tuesday of the semester test for you to upload your honesty declaration. But that's it. There's nothing actually due on Friday. All right. So we've seen functions calling other functions. You've seen it all the time, in fact. But you can, very interestingly, also have functions that call themselves. This is a phenomenon known as recursion, and you can use it basically to create the same sort of repeated behavior as you would get in a loop. And in fact, in pure functional programming languages, you can't have normal loops, because pure functional programming languages are built around the mathematical definition of a function. And in mathematics, if you define, let's say, a to be equal to 1, you can't later on change it and say now a is equal to 2, because it's a definition, not an assignment. So you can't have a loop with a loop control variable that changes values, because strictly speaking, there are no variables. Everything is defined or undefined, but no definitions change. So in those languages, the only way to get repeated behavior is to make use of a function that calls itself, or a set of functions that call each other, and that phenomenon is known as recursion. So in the same way that if you have a loop, the loop needs some situation in which it's going to stop, a terminating condition that will make the, for example, Boolean expression in a while loop become false, or the test for the end condition in a for loop become false, or if it's a collection being processed with a range-based for loop, then obviously the collection is a finite length, so eventually it ends. So there needs to be something that will stop a normal loop. In recursion, you've got the same situation. You need a simple case which will stop as soon as the basically the simplest version of a problem, which you can solve trivially. And the normal idea with recursion is basically you define a problem in terms of itself, but each step in the recursive function process is a simpler version of the problem until you get to the simplest possible version of the problem, which is very easy to solve, in which case you don't need to do anything. And that's your base case. When you reach that condition, you don't have a recursive call and the cycle is broken. So that's basically this. At least two portions is the base case, which doesn't have the function calling itself in it, and the recursive case, which does have a function call to the same function within itself. So addition of a sequence of numbers can be looked at as a recursive process. If you think of it 1 plus 2 plus 3 plus 4, you could easily break that down into a series of smaller chunks. If I add 1 to the next element in the list and then add to the remainder of the list and so on. So let's say you only have the ability to add two numbers. You don't have any ability to add a sequence of numbers. You could still break it down by saying 4, in this case, for example, 4 plus whatever the result of adding 3 plus 2 plus 1 is. Okay, that's fine, but what's adding 3 plus 2 plus 1? That's 3 things. We can't add 3 things. Fine. It's the result of adding 3 to 2 plus 1. We can do 2 plus 1. That's adding two numbers. We know how to do that. So we add 2 and 1 together. That gives us 3. And then we can add 3 and 3 together. That's fine. We know how to add two numbers. That gives us 6. And then we can add 4 and 6 together, and that gives us 10. So if we were ever in a world where you could only ever add two numbers together, you could recursively solve the problem of adding sequences of numbers together by simply treating it as two at a time until eventually you get to the smallest base case. You can solve that and then unwind until you've added all the numbers together. Is it as efficient as a loop? Definitely it's not in that case, because you've got a lot of extra steps that are required, but it's still possible. So if we wanted to implement that in C++, this gives us an example of the structure of a recursive function. We have the function itself, add sequence, takes in a number n. It returns an integer, tests to see if it's n is 1. Basically, have we reached the simplest possible case, in which case we just return that number. And so this is the base case. There's no recursive function call here. And then in the else portion, this will be the recursive case. There will be a recursive step here. So here we're saying we're going to add n to adding of the sequence and then 1 less. So we are assuming that it's a counting sequence, 1, 2, 3, 4. And so we are now reducing n by 1, which means that n will get closer to this base case at each step, and eventually it will reach 1, in which case there will be no recursive call, and then all of the values can be evaluated. So what actually happens is that at each step in the function call, a partial copy of the function exists in memory in a data region known as the stack. And every time we call the function on itself, a new copy of that function's variables and parameters and return value are placed on top of the stack, which then grows until eventually it reaches the base case, in which case there's no recursion, and then it can start answering the questions. So that's basically where we reach here. We return 1. Okay, 1 plus 2 is now 3. We return that 3 plus 3 is 6. We return that 6 plus 4 is 10. So every time you call a function on itself, or indeed every time you call any function, you actually use up a little bit of memory on the stack. And you can think of the stack as kind of like being a stack of plates. you couldn't grab something and remove it from the middle of the stack of pastes. You can only ever manipulate things at the top of the stack by adding things on top or by removing things from the top as well. And this is how the copies of the function, they're actually called stack activation frames, are put on top of each other in a pile, in a sense, in memory until you reach the base case and you're done. So this does imply that if you don't have a base case, you've got the sort of functional recursive equivalent of an infinite loop. But unlike an infinite loop, which can literally go on forever, infinite recursion will run out of memory eventually. And I'll show you examples of those now once I've taken a look at what questions have been asked. N is equal to 1, don't know. So remember, we've discussed this. The braces are optional if you've only got one statement afterwards. We typically will write it. The only reason I did leave it out is because it's already takes up all of the space there. But if you don't have the set of braces, it'll just take the next statement as being inside that if statement. So because there's only one statement here, it doesn't matter. Here there are two statements, so the braces are required. Equals equals is the equality operator, so please make sure to revise all of the work leading up to this point. It's the difference between storing a value, which is assignment. Okay. So bival functions eat up more space than biref. If you want a general rule of thumb, then the answer is yes, because by value will make a copy of the data and send that copy off to the function on the stack, whereas the biref will just send the location in memory where the data is. And unless you've got a very small data type, which is the same size as a memory address, it will take up more. So in general, yes, or you can use that as a rule of thumb. All right. Yep. So those people who've answered have answered correctly. That's excellent. Yep, perfect. That's all good. So some people definitely know their stuff, and I'm looking forward to some good results from those people in the semester test. That is exactly right. So let's actually do a quick example. Code blocks, I suppose. Although this is clearly from Visual Basic using the bival keyword and biref keyword. We don't use those keywords, remember, in C++. We use the ampersand to indicate whether something is a reference parameter in the parameter list. But the principle is still the same, still identically the same. Right, so let's do that. Desktop, I suppose. All right, so let's do let's basically do an infinite loop, a regular infinite loop. Let's say while true. Oops. And we'll just see out something. And you'll be unsurprised to learn that that will just go on forever. But if we try to do that recursively, so let's actually have it return a value. I want to force it to try and use something up on the stack. What can happen is sometimes the optimizer is very smart, and it is possible, theoretically it's possible in all cases, but some of them are much harder to work out. But it's possible to convert recursive function calls into loops, and the optimizer might do that behind the scenes, in which case you won't see the memory eating behavior of the recursion here, because the optimizer fixed it in the backend and converted the recursive function into a loop. So I'm going to try and force a situation where that won't happen. So here there will just be a recursive case and no base case. So hopefully we will get an issue there. So let me also even just output the final result of that just to force it to not optimize it away. Let's try. really matter. This should run for a bit and then stop. Let's see. I didn't do the recursive call, so it ran immediately. So let's not do that. Okay, hopefully it will run out. Let's see. Might have gotten me. Let's see, so we're not using the value at all, and it doesn't matter if the value overflows. Let's see if we can stop that now. It's just going to run indefinitely. It's too smart for me. Let's leave it running in the background and see if it eventually does stop. But theoretically, unless the optimizer has fixed it for me, every time we do this function call here, we use up a little bit of memory. And eventually we should run out of memory on the stack. We did eventually. So what's happened here is that, think of it like this. Every time the function calls itself, a copy of its values and return a memory address and all sorts of things get put onto a pile, like a pile of plates. And eventually this pile of plates grows until it hits the ceiling. That ceiling is basically a portion of memory that splits the memory of the computer into two parts. Now there's the stack allocated memory, which is where all of the local variables that you see and local expressions and everything like that exists. Well, it's not maybe such a great example, but things like that exist. And any local variables you create inside a function will live on the stack. And you don't have to worry about them. They last as long as the current block that they're in, and as soon as the block ends, they disappear. Basically, they disappear because they're removed from the top of the stack. So you can think of a plate being taken off the stack of plates. So every time this function repeats, it's going to add a new stack to the plate and never take one off. So it's going to eventually hit the ceiling. And that ceiling is a line that separates the stack in your memory from what's known as the heap in your memory. And the heap is where very long-lived values that are under the programmer's control exist. And after we finished this first semester test, we'll start looking at memory in more detail, and we'll see that the heap allocated values, the programmer must ask for them, use them, and then give them back. And we can't have this automatically managed memory intruding into the same part of memory as the programmer managed memory, because the compiler and the runtime environment can't predict how long something is going to live that's under programmer control. It doesn't know what logic they're necessarily going to use to remove stuff. So if the stack and the heap weren't separated, these values would overwrite the memories that were allocated by the programmer. So once that stack gets too big, once it passes that imaginary line, basically once the stack of plates hits the ceiling, your program has to crash, because now it can't keep allocating memory without potentially overwriting values that the user or that the programmer has under their control. So when that happens, it's called a stack overflow. And there's a very famous code website called Stack Overflow that makes use of that as the inspiration for its name. And it's definitely a place you should not copy code from in this course unless you want to have a very bad time with student disciplinary services. All right. I'm not quite sure what you mean. Okay, so what dangers do infinite loops have on devices? If someone accidentally makes an infinite loop, it's bad because it's sitting there doing nothing. So it could be blocking input outputs, it could be using energy inefficiently, and so on. But there are valid, correct places for infinite loops, such as any process that runs in the background, like Dropbox or anything like that. That is basically sitting on an infinite loop because it must only end when the program tells it to end, not when some predefined condition ends. Move semantics in C++ is actually technically beyond the scope of this course. Remind me again in the second semester, and I'll do an optional extra class on it, because technically all you need to be able to create the data types in C++ required for the course are the copy oriented semantics. Technically, that's outside of the scope, but do remind me. I actually have no issue discussing it, but I'll do it as an extra video rather than as a part of the course because it's not in the scope. Rec was just a name I meant. I just called it rec to show that it was a recursive version of the process. So it's got no special meaning. Is it bad to declare variables outside of main? Yes, it is. We only declare constants and function prototypes and type definitions outside of main at this point. Yeah, so we're not going to do the only thing that we want different functions to have direct access to outside of parameter passing is constants, because it's very difficult to write what they call thread safe code if you have shared state amongst functions, because if a program is running in multiple threads, which you'll learn about in the second semester, in your second year, they could be interrupted at any point in time, and they could be interrupted halfway through modifying a shared variable. So shared variables are actually a very bad style of programming, and we don't do that. Only constants are safe to place somewhere where they're accessible to all of the functions in a program. So it's a good question, but we deliberately avoid that style of programming. So the stack refers to, think of memory like this. Think of memory as a bunch of think of it like a string or an array, a container of some sort, going from 0 up to some maximum. Every position in the container has a number, so 0 up to the length of your memory minus 1. But we have two different lifetimes for values that are in memory. One set of values must be automatically managed by the environment. Those are the ones that are local variable stuff where the compiler can tell where it needs to die. So for example, this A needs to die over there. End of story. It's very easy. Then there are the other sets of values that the programmer must decide when they come into existence and when they leave existence. The compiler can't know what that logic is going to be. So it keeps that container split into two portions. The stack, which contains all the automatically managed stuff, and the heap, which contains all the programmer managed stuff. Technically, it's not called the heap officially. It's officially called the free store, but almost everyone calls it the heap. And that's basically what that means. It's just different regions of memory in which values of different lifetimes are stored. So it's a good question, but yeah, it's not a set of instructions per se. So recursive is when a function calls itself. So here is a function called rec_a, but you can see inside rec_a, it's calling itself. So the flow of control will be, I arrive here, I move to there, I move to there, I move to there. Oh, I'm calling myself. I jump back, and then jump back, and then jump back. And every time it jumps back, it's adding a copy of the values that it had at that point in time onto this pile of plates, if you want to think of it, each plate being frame activation, and they are using up a little bit of memory every single time. So that's basically what recursion means. It's when the function calls itself. All right, let's carry on. Let's see what else there is. No, rec was just for recursive. We actually will use the rec prefix for variables to refer to records, but this was just a name for the function. So that's all it is. So it's this. You don't need to name your functions that. I'm literally just doing that for that example. Does the heap space contain globals? Technically, there's actually three areas. There's the global area, which contains things that last completely outside of programmer control for the entire duration of the programmer. So technically, there's three areas: there's the heap, the stack, and then the global area. When you do assembly language programming in your third year, you will store things in the global area. Things in the heap space are so mutable means changeable. So basically, the question is asking, can you change the values there? You can, and as we'll see, yeah, they definitely can be changed. So recursive brings a stop to the code. It's the base case that stops the code. So if we take a look here, the base case is the branch in the logic in the code that doesn't contain the function calling itself. So add sequence here, add sequence there, but in this branch there is no add sequence. So that's what stops the recursion being infinite. Oh, that's very funny. Okay. So the n+1 actually wasn't necessary per se. I probably could have gotten away with just passing n like I did originally. I'm just trying to do as much as possible to stop a clever optimizer from realizing, hey, that value doesn't change, and then not doing the work. So I didn't seem to be working, but maybe if I didn't leave it running long enough, the +1 was just there to make it difficult to optimize. But let's just leave that running and see if it crashes as well. All right, let's carry on. Okay, so this is just showing you the evaluations and where we are in the process. Basically, each of those steps that we showed here when I highlighted the different steps in execution. That's just showing each of the activations of the function and what the values are, and then eventually it stops. So this is considered the sort of standard example for recursion. It's the factorial calculation of factorial. So factorial, as you may know from mathematics or from statistics, if you do mathematics, if you do combinatorics, is defined as follows. Let's say we had 3 factorial. That's defined as 3 times 2 times 1. 4 factorial is defined as 4 times 3 times 2 times 1. So you could create a loop that calculated these fairly easily. You just loop down until you hit 1, and you multiply and store the combined results at each step. So that's fairly easy. But an interesting thing to note is that 4 times by 4 factorial, let's say, 4 factorial is equal to this, but you can see that actually, wait a minute, 4 factorial is equal to 4 multiplied by 3 factorial, and 3 factorial will be equal to 3 multiplied by 2 factorial, and so on. So if you define 0 factorial as simply being 1, you can have a base case for that logic, and that's exactly what this stepwise function shows. It shows that if n is equal to 0, then n factorial is equal to 1. Otherwise, it's equal to n minus 1 factorial multiplied by n for all n's greater than 0. Obviously, this function will only work on positive numbers, or 0 and up. So let's implement that. This is sort of the canonical example. Okay, so what did it say? We needed a base case. So if n is equal to 0, then we will return 1. Otherwise, what will we need to do? And if it does bother you, we can include the full set of braces. It's never wrong to do that. You might, when you're coding, decide later on, I'm going to go back and add more statements to that list, so that saves you some time. Otherwise, we will return n multiplied by the recursive call to our function n minus 1. Strict, I suppose, really should do this if you wanted to make sure it was never going to be negative and didn't want to add any code for testing that. You could, of course, make everything an unsigned integer, and then we could work out something like 5 factorial is equal to and let's run it. No, this thing crashed. It did, so it wasn't able to optimize that away. So we did eat up all of the stack space and create a Stack Overflow. And here we have it. And let's run it. And there we've got our answer, 120. So this is not a super efficient algorithm, but it is nice in the sense that it matches the mathematical definition exactly. Why is it not efficient? Because it's actually recomputing some values, like, it'll compute 3 factorial once and then again and then again. So it'll recompute these values a couple of times, plus it uses memory unnecessarily. So it is less efficient than a loop that would have done it. Technically, this is an example of a recursive function of the form known as a tail recursive function, because the last action in the recursive function is to call itself. So if you've got a function that's in the form of a tail recursion, it's then very easy to convert into a loop by a smarts compiler. I don't think I have my compiler optimization settings are set very high here, and I'm not sure if C++ does conversion from tail recursion to a loop automatically, but it is possible in some situations to do that easily. Okay, so let's move on. So m+1 makes it finite. So as you saw, it didn't have any impact in how that function ran. The int a is equal to 0 is also just part of me putting stuff in the, well, I've taken it away now, but putting stuff in the algorithm to try and make it difficult for the optimizer to optimize it away. I just wanted something that was definitely going to use up a bit of memory every time the function called itself. So that's, okay, it's a little complicated, but if you imagine a world where there's only one computer, or a computer which is only running one program, then there is only one stack. But obviously in a proper multitasking operating system, each program has its own set of memory that it's been given, and each of those has a stack and a heap portion. So it's the job of the operating system to divvy up the real physical memory amongst the different programs that are running. You'll learn all about that in Computer Science 3. So it's a good question, but it's way out of the scope of this module. We'll talk about functions working with other functions, and the answer is no, it won't get invoked automatically. So yes, in a way, the base case is what tells the function how many times to run. So every time the recursive case occurs, this value here must get closer to the condition that triggers the base case, and that's what determines how many times it runs. Yeah, okay, that was correct. So unsigned, we discussed this in the theory, remember, when we spoke about the representation of negative numbers in binary through either the use of sign and size or the use of 2's complement. So unsigned integers basically disable the support for negative numbers on an integer and make it have twice the positive range at the cost of not having any negative range. But since these values can never be negative, because factorial is not defined on negative numbers, that's what that means. Okay, good. These are two different levels of complexity, but explaining the same thing, and so on. Yeah, look, it's difficult for most situations. Recursion for a normal programmer in what we call an imperative programming language, which is most programming languages, recursion is something you do only if it's necessary. So if a problem is defined very elegantly in terms of a smaller version of itself, recursion is a very nice tool to have at your disposal. If it's not, then you typically will spend more effort for worse results. However, there's some styles of programming, like functional programming, and some programming languages, like Haskell, for example, which don't support mutable data at all. So there's no such thing as a variable. Those have to use recursion. I'm not quite sure I understand what you're saying. This is not relevant to the current problem. We're not dealing with comparison of real values, so I don't understand your question. Foo is nothing. Foo is just a default name for a something you couldn't be bothered to give a name to. So it's very common if you've got two things to call one foo and the next one bar. It's just a convention when you don't name things. I think you might be confusing B.A. Baracus, the character, with Mr. T, the actor. Remember, they're different things. The actor's name is Mr. T. The character's name is B.A. Baracus. All right, Let's continue. All right. So we basically just implemented that, and you saw how it works. So uncontrolled recursion is practically finite because you use up a little bit of memory every single time you do recursion. Another very common recursive example is the Fibonacci sequence, which is a sequence that occurs in nature all over the place. It's very closely related to a ratio known as the golden ratio, which is used a lot in architecture and things. Basic sequence is as follows. Let me get this right. And so on. So if you look closely, you can see how the sequence works. It's simply the sum of the previous two terms. So 0 and 1 gives me 1, 1 and 1 gives me 2, 2 and 1 gives me 3, 3 and 2 gives me 5, 5 and 3 gives me 8, 8 and 5 does give me 13, and so on and so forth. So you can see how the sequence would progress. Right. Sorry, 21 and then 34. But it too is defined in terms of itself very nicely, because you can define the first two things with a straight up definition. So if it's 0 if n is equal to 0, or 1 if n is equal to 1, but then you can define all subsequent terms after that point recursively. So this is there's two base cases, 0 and 1 are both part of the base case, and then there's two function calls within the recursive case, one to n minus 1 and the other one to n minus 2. So you can implement this function as follows. Simply test to see if you're in one of the two base cases, so n less than or equal to 1, return whatever it is. Otherwise, do the recursive calls for n minus 1 and n minus 2. You can see that this basically is a one-to-one mapping between the mathematical definition of the Fibonacci sequence and its implementation in code. There's no, I mean, obviously it's been written in C++, but you can very clearly see those two things working on. Okay, you can work through the evaluation of that if you want, but that's enough for that. Let's answer some more questions and see where we're at. Yes, it is very, very interesting, the Fibonacci sequence. It like occurs in things like how seeds are positioned in a sunflower and all over the place, as well as cropping up in human architecture and so on and so forth. It is very, very, very powerful. I mean, how important you view it depends maybe on whether or not you're a mathematical realist or not, but it's definitely something that crops up a lot in a large number of very different fields, and I find that fascinating and interesting. But yeah, that's that. Let's quickly take a look at compile time functions. You've already actually seen them. We actually introduced them to you fairly early. Let's say, for example, we wanted to have a value that didn't change. And this is a dumb example, but let's say 8. We know 8 doesn't change. 8 always stays 8. But let's say we didn't want to have to sit out, take out a calculator, work out what 2 times 4 is, and then put a proper constant in our code. Let's say we knew the formula for working out 8 by 2 times 4, but we didn't want to have to do that work. So we could write a function that did multiplication and then assign that value to a constant, and then it would stay constant for the duration of the program. But the problem is this actually runs when the compiler first starts, or when the program first starts up. It'll actually call this function and do that calculation. Now this is very simple. Multiplication isn't difficult. But what if it's some complicated constant that you have to work out, or complicated value you have to work out that won't change under a certain circumstance, but you don't have to recalculate it every time your program starts up. Let's say when you're compiling a program for a specific computer architecture, there are some complicated offsets and various values that you need to work out, but you only need to do it once at compile time. You don't want to have to make your programs running on that architecture slower by having them recalculate everything when they start up. So you want a function that runs at compile time effectively. Right, so it looks like it's working here, but it's actually running unnecessarily all the time. And that's when modern C++ introduced const expressions. So basically it's like a constant, except it can basically also be a function. So in this case, doing this won't really have any effect because it's still going to run that again unnecessarily, even though it knows that that's supposed to be a constant expression. So what you can do instead, effectively, even refuse to compile because this is not constant necessarily. This has to be constant, we've said. So if we do run it again, but label the function itself as a constant expression function, now it knows, this has to be something I can work out at compile time. This has to be something I have to work out at compile time. That's okay. It all lines up. Everything's compile time. So then it will do the calculation at compile time once, not every single time you run the program. There's restrictions on constant expressions. They can only have a single return value, can't be void. What's the point? You're trying to work out a value. They can't have local variables because think about it. We've just discussed where local variables are stored. Like, for example, that A that was asked about, they're stored on the stack. There's no stack anymore at compile time because the memory that's being used on the compiling machine is not the same memory as going to be used on the system where this program is going to be running necessarily. Most programs are not compiled by their users. So you can't have local variables. And because you can't have local variables, you can't really have loops, and they may not have any side effects because it's obviously something that has to run at compile time. You can't change a variable somewhere or do anything else like that. So if it's got these restrictions, how can we use them if they don't have loops? Well, we've just seen you could actually use them through recursion because they can be recursive. So here's an example of the factorial function, but as a constant expression compile time function. And we've collapsed it into being a single statement by using the selection operator that we discussed earlier. So here is the base case, right? So if n is greater than 1, we will then do the recursive case. Otherwise, if it isn't, we will do the base case. So its value will take on the value of 1 or recursively computing factorial in the recursive case over there. So now we could say we have a constant 5 factorial, calculate 5 factorial, and then only do that once at compile time, not every single time the program runs. So this is definitely a good place to end. And I'll answer any last questions you might have. So it's like yes, it's not a bad way to think of it, a pre-program. It's something that it runs when the compiler runs and calculates whatever values you need. And like the preprocessor does other things. So you can think of it, these sort of things were actually originally done using the preprocessor, to be perfectly honest. Before constant expressions were introduced, it was possible to write very complicated macros that would do the calculations you wanted at compile time. Constant expressions were meant to be a way to replace that with stuff that included proper type checking and all the normal C++ stuff that you might want. So it's exactly that. So you can, it's 100% okay to use a constant expression in a normal runtime function. It's not okay to do the reverse. You can't use a runtime function in a constant expression function because then it can't guarantee that the values won't change. And that's exactly what happened in that example here, where we had times is not a constant expression function, so it gets evaluated at runtime, but this expression over here needs to be evaluated at compile time. And there's a mismatch here. There's no guarantee that this is going to be the same every single time. And that's why the compiler didn't accept it. So it was a very good observation or question there. But yeah, so it's fine the way you've put it, but the reverse is not fine. Yeah, so I'm glad you asked here. So all of this stuff is what we call modern C++, and it's not on by default. So if you are running your program, you sometimes need to turn it on. So you go to build, you go to project, you go to build options, and then you pick the highest of these things you're comfortable with. So typically it'll be something like C++ 17 will probably be the highest one. Exclude things like 1990 and 1998. Those are the older ones. So anything, basically this represents the year in which the standard was released. So 2011, 2014, 2017. 2011 was the big year, the boundary between modern and classical traditional C++. And 14 and 17 and now 20 have just added small improvements to it. But if you want the modern C++ features, pick something greater than 11, whatever the highest thing your compiler supports, and then it should be quite okay with constant expressions. So that was a very good question. So 17, CodeBlock 17 should have it. It's obviously been around for a while, but it's not on by default. So good question. Okay, so if you are compiling from the command line, then you would do this. So good question. So you'd go C++ or G++ minus std equals whatever version you wanted, let's say bare minimum C++11, and then main.cpp, and then you're good to go. If I didn't include that, it should yell at me. And I didn't have a constant expression in there, but that's how you would manually add the flag. Okay. When you compile a program, what's the first function that runs? That's an interesting thing. So if you've got a set of constant expressions, which one gets executed first? It wouldn't. There is no main for constant expressions. So basically, it would create. It's technically known as a directed acyclic graph, where basically every function that depends on every other function is. You can sort of think of them as circles with arrows pointing to each other, and then it will find the one that is the one on which all the others depend. If you've got like a cycle in your graph of dependencies and they all depend on each other, it won't be able to compile it. So it's a really, really good question. Does constant expression help with storage usage as well? Yes, it does. Because the value is worked out at compile time, it's literally baked into the C++ executable directly. So there's no need, it's stored as a single value. There's no need for any other storage that might be used during runtime to work it out for the non-constant expression versions. So it's both faster and uses less space. It does make the compile take longer. So the theory is that you're willing to trade an extra long compile time for a shorter, faster running program, because most programs should be compiled far less often than they are run, right? So it's worth the trade-off to make the compile slower for a faster and more efficient executing program. So I think we're done now. So I'm going to wrap it up there because we're way past time. Thank you, everyone. That was very good discussion. I asked some really good questions. Study hard for the semester test. We will still have Monday, of course. There is a practical on Friday where you can ask questions. There will be an assignment due on the following Tuesday just for you to upload your honesty declarations. And that's about it. So thank you very much. Have a good evening. I wish you all very well.